great. Such different perspectives. Although I think there's a lot of value in it, but
yeah, definitely. Yeah.
So you can generate the value, just won't get it published.
But maybe, like, for instance, like the government people don't, maybe, I guess some of them are academics, so that maybe they want to get it published. But otherwise, like, maybe the value is just like getting stuff done. Like maybe you need government initiatives or changing policy, or these are slightly different objectives than just getting it published as well, right?
No, true.
yeah, fair enough.
Hey, looking at the time, 1 past now. Yeah, I guess we can still wait for just 1 or 2 minutes for people to join.
Okay.
But
Should I
don't know.
And share my slides, or should I wait? Should we wait? I don't know.
I would share them already.
Okay.
Yeah.
Why not? I think also. And should we also get the? So Robert, are you handling the YouTube? Good. All right. That's always good to know. Yeah. So I guess also for all the people that already joined, we will record this and stream it on YouTube. So if you're uncomfortable with being recorded, please turn off your camera. And I suppose in any case, turn off your mic. So I will also lead by example.
Okay. Wait, I might have to rejoin. I'm trying to change my sharing preferences very quickly. Sorry, this is my new DeepMind computer.
No worries. We've had it a couple of times, indeed. I think so. Shaigan, can you remind us the exact procedure?
Is it a Mac?
Yeah, and it says Google Chrome will not be able to record the contents of your screen until it is quit. So quit and reopen or later.
Yeah. You might have to just do a quick reboot of that.
Okay. All right. I'll be right back, guys.
No worries.
Okay.
See you in a bit.
See you in a bit.
Yeah, I guess that's fine, right? You can stop and then start again when Kalisha comes back.
Good. Okay. Unfortunately, I can't see you guys anymore.
We're still here.
Okay, good. Good. So you have to like say something whenever if you have any questions. Actually, I'll come back.
Sounds good.
So I'm back on the screen right now, but let me know when to get started.
Perfect. I'm just going to kick off the recording in Google Meet as well. Sometimes the YouTube live stream goes down, so we just want to have just a backup recording. Let's wait for that to start. Shall we get started? I think we're at the 10:05 point. Perfect. Yeah, so welcome everyone to another session of the COMARL virtual seminar series. This is actually the last session of this season. And then I'm sure we're going to have future sessions as well. So, keep an eye out on Twitter and the group for more info on that in the future. Franz already mentioned a couple of the practicalities before we start, but just for those who joined a couple minutes ago, we are streaming this to YouTube. So if you're not comfortable with having your camera on, please turn that off. And then please also turn off your mics just to minimize any background noise. And then we will have a chance for a Q&A. Usually for any quick questions, please feel free to use the chat panel that you can see on the bottom right. There's a little chat icon just for like clarifying type of questions. But otherwise, for kind of longer questions, you can use the Q&A panel in Google Meet. So it's the little panel with the little polygons on the bottom right, and then click Q&A. So we'll hold those for the end, and you can kind of upvote and downvote questions, and we'll manage those right at the end. So that's all the kind of practical details. Today, it's my pleasure to announce that we're having Kalesha Bullard as our speaker. So Kalisha is has recently joined DeepMind as a research scientist, and she's working on the multi-agent team. She focuses her research on a large number of topics, primarily on autonomous decision-making for artificial agents in multi-agent settings. Her work has previously targeted models and algorithms for enabling agents to learn through interactions with one another, and also interactions with humans in some cases as well. Prior to joining DeepMind, she was a postdoc at Facebook AI Research, where she was conducting research on approaches for zero-shot multi-agent communication, and also work on populations of embodied agents as well. And prior to that, Kalisha completed her PhD at the School of Interactive Computing at Georgia Tech, where her research focus was on interactive robot learning and active learning. And most recently, Kalisha was a co-organizer and program chair at the NeurIPS 2021 Cooperative AI Workshop, which just happened a few days ago. So it's our pleasure to have you, Kalisha, as the presenter for this last session of COMARL seminar series this year. Thanks again so much. The floor is yours.
Thank you so much. Thank you, Shay. Again, I really appreciate the great, kind introduction. And I'm really excited to be here and kind of chat with you guys about some of the research that I've been working on recently. So thank you all for inviting me again to give a talk. And, you know, today I'm going to discuss my most recent body of work that I did during my postdoc at Facebook AI Research on zero-shot emergent communication. I hope to continue building upon some of these ideas as I move forward in my role as a scientist on the multi-agent team at DeepMind. So I'm really keen to share with you guys the exciting progress we've made thus far and discuss thoughts and feedback that you may have. So I just want to start with, motivating multi-agent systems, which I guess this audience already completely understands that, but kind of my interest in multi-agent systems. I think that when we think about like moving forward, this technology is expected to become pervasive and ubiquitous throughout society. And multi-agent systems has a diverse set of ways that it can look. So, you have the self-driving car in the top left, you have humans and robots trying to interact and coordinate effectively in a factory setting in the top middle. Even traffic light systems, which are fully artificial multi-agent systems, I think are relevant to this general space. And then on the bottom right, a human robot system, which is something that I thought about more in my PhD. But I think these images also show the heterogeneous nature of multi-agent systems and it coexisting and the coexistence in shared environments. So in general, my research really thinks about multi-agent systems that are in cooperative settings. The setting could be fully cooperative already, or it can be the case that we want to incentivize cooperation, but really this goal being cooperative multi-agent systems. And I think that this comes from this idea that the real world, again, is inherently multi-agent. And if you think about biological systems, then oftentimes the way that we're able to navigate real world environments, and even in the ways in which we evolve effectively, we need to be able to cooperate and coexist and coordinate with one another. So I think that communication and coordination are also going to be a necessary capability amongst AI agents and human agents as we move forward with multi-agent systems in society currently, like technological multi-agent systems. So here's some relevant application domains that I find quite interesting, but the ones that I will motivate this talk by more so is the self-driving vehicles or robots in human environments. And the talk is, the work is still more abstract, but it's motivated by, I think, some real world domains where we could potentially benefit from these kinds of ideas. So imagine that you have these embodied agents operating in a shared environment. And I want to motivate first why multi-agent reinforcement learning is kind of the primary family of methods. So the question here is, how could these agents learn to communicate in order to aid in coordination, like the different, presuming these might be like an autonomous vehicle system, so these might be self-driving cars and, some kind of human agents. So you might say supervised learning from data sets or imitation learning from demonstrations would be a viable approach. And one challenge there is that supervised learning would require huge existing data sets for each agent embodiment. So if you have different types of cars, you're going to need different data sets for the different types of cars and the different types of communicative skills that you want agents to learn. Multi-agent reinforcement learning, however, provides this opportunity to allow agents to learn a protocol solely through agent-agent interaction. So instead of having to collect these huge data sets for every agent embodiment, for every type of communicative skill, we can turn compute into data through the agent-agent interactions. But one question would be, should these agents have to train with every potential partner that they could encounter in order to infer a more general communication protocol? And I want to frame this talk around this idea that even though multi-agent reinforcement learning is a powerful mechanism, a key consideration in learning protocols is that we want to be able to generalize to unseen partners. So we don't necessarily want the agents to have to, kind of train with every other agent. And this is, so this, in this application, this might be cars that the agent has not previously encountered, but still needs to be able to signal to. So, so with that, this work is a collaboration with collaborators from FAIR. Or like I said, this is for my postdoc. So this work was done when I was still at FAIR, and Jacob was also still at FAIR. Okay. So these are the kind of two manuscripts that I'll be referring to in the talk. So this general motivating research question is, how can general communication skills emerge in embodied agents? And in particular through action. So we're not talking about necessarily communication through language, which is a traditional way we might think about it. We're talking about communication through action and using this idea of the embodiment as motivation for this. And it's motivated by the idea that embodied agents such as humans and robots inherently communicate through movement. And so if we want to move towards human level intelligence, we need to enable artificial embodied agents to communicate through this more realistic channel. It's also, it can also be motivated by the idea of implicit communication. So, this communication is not always explicitly spelled out through language. We often communicate implicitly, again, through action. So I think that's another way to think about motivating this kind of work. So learning and communication protocol. So what is the underlying idea here? So let's say you have a population of agents. Here you have a blue, a green, and an orange, and they have some set of communicative goals that they have been given a priority that they need to be able to communicate. The underlying idea is that each agent in the population must learn to generate messages for every communicative goal in the library. So the learning problem then is to for every agent to learn a policy mapping the set of communicative goals to the message space. And a concrete example might be that the goal is to greet or like to say hi, and the message might be to wave. So, so this is just kind of a graphic of single agent RL, where you have this learning agent who is typically the assumption is that it's interacting with this non-stationary environment and able to get reward, able to take observations and take actions in order to change the state of the world. And the goal is to maximize this long-term return per episode. But the way that we want to change this from multi-agent RL is now the environment is non-stationary because the other agent is learning. So even though the physical environment or virtual environment, we're not assuming that is changing since the other agent is learning, from the perspective of learning agent I, the world still seems to be non-stationary. And so this is going to, increase the complexity of the learning problem. And so the way that we instantiate this in protocol learning, and the way that's typically been instantiated is through these referential games, which is a type of multi-agent signaling game. And so the premise of the game is as such. You have a sender Alice that receives some communicative goal G as input, a priori. And Alice must find a way to communicate a message M to Bob such that Bob can correctly predict what the communicative goal is. And then there's a shared return based upon how well Bob is able to infer what Alice was signaling or referring to. Two important assumptions persist in this typical problem setting. One is that it's typically assumed that it's there's a discrete communication protocol, so every message is an individual action coming from a set of actions. And it's also typically assumed it's a cheap talk setting. So the cost of sending a message or the cost of generating a message is zero. So this is not intended to be, an exhaustive visualization of all prior work, but it does give a sample of much of the prior work in multi-agent communication literature in this deep learning era, so over the last 5 years or so. And it's intended to briefly illustrate kind of where recent prior literature has focused. And in particular, most of the prior work has focused on these typical assumptions. And so we want to relax both of these because these both present limitations when you think about the case of embodied agents. And I'm going to start with the assumption of cheat talk. So our problem setting is one of zero-shot coordination, which was introduced a couple of years ago, or maybe a little over almost 2 years ago at ICML. And the assumption in the zero-shot coordination setting is that it's a fully cooperative setting, and that the goal is for agents to coordinate at test time with other agents who have been independently trained, so essentially with strangers. In this work, they introduced equivalence mappings of policies, and they formalized this idea of symmetries for the underlying DECPOM DP. So I'm not going to go into details about the equivalence mappings of the symmetries in this talk, but we will build upon these ideas. So in this work, we formalize this problem of zero-shot communication, which is an instance of, which is an instance of the zero-shot coordination problem setting. And the coordination goal is to learn a communication protocol that effectively generalizes to unseen agents. So now I want to go ahead and formalize this. So typically it's assumed in this zero-shot coordination setting that agents train through self-play. So here you have two different pairs of self-play agents. And so I'll just talk about briefly go over the notation with the green pair. So we're assuming that we have two agents, a sender and a receiver. And the sender, let's call it pi1, gets some communicative goal as input and can also take a private observation O1, and it can take some action A, and the action is assumed to be a communicative action. So I should say here that there's an assumption that in this work, we're just really looking at communication as the task. So, one thing that could be a future opportunity is to integrate this with, some coordination task or some task in the environment. But here we're only considering the task of communication. So the action is a communicative action that the sender takes. And the receiver can observe that action. It can also take a private observation from the environment, and then it makes some prediction about what's being communicated, and the reward is back propagated. So here you have two independently trained self-play agents, and then at test time, what we want to do is effectively swap agent partners. So we want to have agents engage in cross-play in order to evaluate zero-shot communication success. And we want to test how well each agent is able to communicate with an agent that they've never encountered before that was trained independently. So you might say, okay, so that paradigm makes perfect sense. So what's the problem with training using self-play? So the challenge is that you, with self-play, you can have many equivalent but incompatible joint policies. And for successful coordination, we need the agents to agree, the agent pairs to agree on a protocol. So here is a simplification of an optimization landscape. And here each red dot represents a communication protocol. So let's say here we have 4 different protocols that are equivalent but incompatible. So let's say one is like a German one, and one is a French one, and one's an English one. It's not necessarily reasonable to expect that. So there's nothing incentivizing agents who start randomly and arbitrarily at different places in the landscape to converge on the same optimum because they're all equivalent. And it's not reasonable to assume that a sender-receiver pair that converges on the English protocol is going to be able to communicate at test time with a partner that converged on a German protocol, let's say. So what we want to do is bias the optimization problem such that we induce one globally optimal communication protocol. And here now, when you have 2 different sender-receiver pairs that have been independently trained, it's still reasonable to expect that a German sender can successfully communicate with a German receiver at test time, even if they never saw each other during training. So that's the underlying idea. And so our general approach is twofold. The first thing we want to do is induce bias in the protocol learning with priors on the solution space. But we don't want arbitrary priors, we want priors that come from the real world kinds of constraints that we expect these types of agents to exist in. And so in the ideal case, that can engender one unique globally optimal protocol, and then we're done. But what we'll find is that it is the case that even when you induce bias through real world constraints, you can have communication protocols that are equivalent but incompatible. So more than one optimal communication protocol. And in that case, what our approach is to adapt the learning objective to learn some distribution over equivalent global optima. And we're going to exploit the idea of equivalent classes of communication actions for this. So for inducing bias, we're looking at priors from real world settings. So the first prior, we have two priors that we use. One is that when you talk about communicating, through action, there's a cost to the physical energy exertion. And so now we're relaxing this assumption of cheap talk. This is a non-cheap talk setting where communication is costly. The other prior that we want to use is in quantitative linguistics, they've commonly used non-uniform distributions in order to represent kind of the frequency that you'd expect of words or sentences. And the Zipfian distribution is one that is popularly used. So we induce a Zipfian distribution over our communicative goals. So when you put these together, what this means is that actions that are the most costly when you put this together, so for example, you would expect something like yes or no as communicative goals to occur more frequently than turn right. So the actions that occur the most frequently in the set of communication actions should be assigned the least cost. So we want to incentivize a minimal effort protocol. Okay, so then you may say, okay, well, what about symmetries and realistic communication? So let's say my communicative goal was go ahead. I want to tell another car it's their turn. So there could be here, let's say there are three different ways of communicating this. One could be that I'm a humanoid agent. So I could wave with my left hand. Another could be that I wave with my right hand. Another could be that I nod my head to say, it's your turn. Oh, I'm sorry, wave with my left hand, like come here. Wave with my right hand to say, come here, it's your turn. Or then like nod my head to say, you go. So if all of these exert the same amount of energy, one challenge is that there are at least three different communication protocols that are equivalent but incompatible, and they're all minimal effort protocols. So if I'm a sender who trained with a receiver, if I'm a receiver that trained with a sender that waved with his left hand to tell me go ahead, and then at test time, I face a sender that nods his head to tell me to go ahead, I'm going to have trouble interpreting that signal because our communication protocols are not compatible. So how does symmetry impact the optimization problem? So the picture that I showed you when I talked about the two priors that we induce, which is about energy exertion and non-uniform distribution over communicative goals. If it is the case that there's no redundancy in the action space or goal space, so every action has a distinct cost, every goal has a distinct likelihood, then there is going to be one unique minimal effort protocol that is globally optimal, and self-play will be sufficient to learn this policy or to learn this protocol. However, if there is redundancy in the action space or the goal space, then this leads to multimodality in the optimization landscape. So if many actions have the same cost, which means they can be used interchangeably, or many goals have the same likelihood. And we're going to focus on action symmetry in this work. And so the challenge here is that there are multiple minimal effort protocols, and so we still want to be able to address this. So I'm going to make this slightly more concrete with an example from a discrete domain that we used in our experiments. So here what we have is, I'm going to explain this game. So we have a sender-receiver pair, an orange sender-receiver pair at the top, and a green sender-receiver pair at the bottom. So the left column is the visualization of the sender policy, the middle column is the visualization of the receiver policy, and the right column is the confusion matrix to show where sender and receiver agree. So I'll start with explaining the confusion matrix. So here, basically what we want to see is probability mass along the diagonal, because that means that this is the greatest probability is where the true intent by the sender matches the inferred intent by the receiver. Then if we go over to the very left column, the sender policy, the y-axis shows the intents. So here we have 5 different intents, 0, 1, 2, 3, and 4. And the x-axis shows the actions that the sender can take. So the intents are the input for the sender, and the actions are the output. So the different actions that the sender can select based upon the intent. Yeah, okay. In the middle column, the receiver policy, the y-axis represents the actions that the receiver can observe by the sender. And then the x-axis represents, and that's the receiver's input. And the x-axis is the receiver's output, which are the intents that the receiver can predict based upon the action that it observed. Additionally, the intents, the number of the intent tells you how its rank in terms of frequency. So intent 0 occurs the most frequently, intent 1 the next most frequently, etc. And intent 4 here, which is has the highest number, occurs the least frequently. The other thing that I want to highlight here is these classes, these E equals, you see equals 0, equals 1. These are energy classes. So basically actions for that are included in equals 0 have no energy costs. Actions that are included in the E equals 1 bracket have an energy cost of 1, and so on and so forth. So there are many different ways to learn an optimal policy here, let's say for the sender. So intent 0 should always be mapped to action 0 because it's the most frequent intent, and action 0 is the only action that exerts 0 energy. However, intents 1 through 4 could be mapped to any of the actions 1 through 4, and you would still have a minimal effort protocol. So both the orange pair and the green pair have learned a minimal effort communication protocol, and we see that they understand each other because all the probability mass is in the diagonal. And so their self-played training coordination is 96%. However, when we do cross-play at evaluation time, the agents actually perform quite poorly. And they've learned communication protocols that are equivalent but incompatible. And actually, if you look at the diagonal on the very right, the only intent they're able to really get correct is intent 0, because there's really only one way to map intent 0. And intent 0 occurs about 44% of the time. So this shows you that the best they can do is guess the most frequently occurring intent. So the question is, how do we address this gap in communication efficacy between training partners in self-play and novel partners at evaluation time and cross-play? So, so the baseline is to train using self-play, and this is the self-play objective. It incentivizes each receiver agent to optimize for an individual, each receiver agent pi 2 to optimize for an individual sender pi 1, which is its training partner. So the two may converge on this left communication protocol, but again, if one of them faces a partner at test time that converged on the right communication protocol, then there's going to be communication trouble. So what we want to do is exploit an idea of equivalence mapping, so equivalent communication protocols using the other play learning objective that was introduced in Hu et al. In ICML 2020, the same paper that kind of defined this zero-shot coordination setting. And what the other play objective tries to do is it modifies the self-play objective to incentivize each agent to optimize for an entire equivalence class of partner agents. So the agent would not only be optimizing for its training partner, but also any symmetry equivalent policies, any of which it could presumably face at test time. So it's maximizing over equivalence classes of policies. And so what we're going to do is propose a new formulation, for using other play for emergent communication, and show how this objective links to information theory. Okay, so first I'm going to do the analysis of the objective function of this other play objective function for the communication task. So pi 1 represents the sender policy, pi 2 represents the receiver policy, and pi is the joint policy. So the general objective for a costly channel referential game would be you want to maximize communication efficacy. So all referential games want to maximize communication efficacy, which is the probability of the joint policy, that the joint policy is able to predict the correct communicative goal G, given some communicative goal G to the entire pair as input. And then since it's a costly channel communication protocol, we want to also minimize action cost. So in each line, the green represents what is changing from the previous line. So here on the left side, basically, I'm just expanding out what it means to be taking the log probability for the joint policy of G given G. So P of G times log P of G for every single goal in the set. And then on the right side, I'm expanding out what I mean by cost here. So for each goal, for each communicative goal, it's going to be the cost of the action times the probability of that action being taken by the sender given the goal times the prior for the goal. So we're going to leave the right side, we're just going to bring that down. And on the left side, what we're going to do is pull out the goals, the prior from that summation. So now we have the probability of this joint probability of the communicative goal and some equivalence class. And then inside our log, we're expanding what it means to have the log of the joint policy of G given G. So really what we're saying here is that it's going to be a product of the two individual policies, the receiver policy pi2 and the sender policy pi1. And this is for every single communicative action. So now, importantly, we have a summation in the log that we want to try to get rid of. So in pulling the summation out, we use Jensen's inequality, and effectively the log of the sum is it should be greater than or equal to the sum of the log. And then on the right side, what I did is just put this in notation, basically. So condense the notation. So we're going to take some expectation of sampling your action from the joint policy given the cost of the action.
So it looks like there's a quick clarifying question. Franz, you want to ask your question?
Yeah, so I guess I missed it, but so you have this P of pi of G given G. So what is G given G here exactly? It's somehow a goal, and then that's translated in a message of G, or?
Yeah, that's a good question. So G given G here is basically saying the system, the sender receiver, the pair is the sender will be given some G as input. And then, so that's the right side, what's conditioned upon, and when you pass, and then the sender will generate some action, the receiver will see the action, but as the output, the receiver will have to predict a goal. So this is for the entire joint policy or for the entire sender receiver system. The input is some communicative goal, and the output is a prediction of the communicative goal. And then
okay, so there's two G's really. One is being received indeed by the sender, and one is sent by the sender. Is that
one is being received by the receiver and one is being sent by the sender. But the reason why I don't have like a G hat or something like this is because the reward is how well the receiver predicts the correct goal, given that the sender had some goal as input. But the receiver is predicting some G hat. But the reward is based upon the probability that G hat equals G. Does that make sense?
So is the act? So then what is A? I guess I thought A was the prediction.
Communicative action. So pi1, which is the sender policy, is going to select some action given a communicative goal G. If you look at like the second sign, the second or the third line with the equal sign. Pi1 selects an action given G, and then pi2 is actually going to get, in this system, it's going to get some equivalence, some action, some equivalence mapping over that action. So basically that action we pass through an equivalence mapping, and then some other action will come out, and then pi2 will see that action and make a prediction about the goal. Which I'm going to explain in more detail
I see. I think I got it. Yeah.
Okay. Yeah, and I do have more. I will go into more depth. I'm just trying to show here kind of what the objective function is optimizing for.
No, thanks.
You're welcome. So basically, so we had a log of a product in the previous line, and so I'm basically just separating this to have a sum of logs. And then there's a couple steps that I skip, but effectively what's important here is that what we get down to is that there's three different terms in this that this objective function is optimizing for. And the first and the third ones are the ones that I really want to draw attention to. The first one being mutual information between the set of goals and the equivalence class over some action for every single action. And then the last one being minimizing effort or cost. And in the first term in particular, what this means is that since it's mutual information, it means it goes in both directions. So if I see a communicative goal, then I should be able with high confidence be able to predict where in the action space should have high probability mass, like which action should have high probability. And if I see a communicative action, then I should be able to, with high confidence, predict which communicative goal is being communicated. So this is what the objective function is optimizing for. And in particular, the question is, how can we obtain these equivalence mappings?
Can I quickly ask, do I understand it correctly that this is not giving extra weight to like maybe more important goals or things like that? It is treating all goals equally?
It's not necessarily treating all goals equally. It's treating the goals based upon the prior. So if you see, like if you look in the top, the second line with the equal sign, you do have a prior for the goals. So it's going to treat the goals, in accordance.
Right, but the prior is like how likely they are, not necessarily like how important is it to get this particular goal right.
Yes, that's a good point. Yes, the prior is how likely they are. So, I mean, and that's something that's come up in previous talks that people have asked questions about. That there's an opportunity there to be able to say, can we incorporate something about the importance of the goal or the salience of the goal? Or something.
Right. Like a normal car versus an ambulance, which is rare but important. Whatever. Okay, thank you for the clarifying.
Currently, that's not incorporated in here. Yeah.
I guess the prior is also one covers the Zipf distribution over the
What? I'm sorry, I didn't hear that. Was that for me?
I think you have to speak up a bit. It's hard to hear you. Can you type the question?
Yeah.
Where does the Zipf distribution get incorporated? Good question. So the Zipf distribution, that is actually, so the Zipf distribution is what gives us our, let me make sure I'm getting this right, not the P of, the Zipf distribution is actually what gives us our P of G. So that, so the prior can be, so the prior can be anything, but this is where we, this is a great point. This is where we use the Zipf distribution. We use the Zipf distribution to induce some non-uniform probability distribution over the goals. And in that case, every single goal has a distinct likelihood. Okay, so so basically, so the question was, how do we learn these equivalence mappings? So Otherplay makes this assumption that the equivalence mappings are given, and this is, in practice, this can be a key limitation. This is a quasi-equivalence discovery, which is the algorithm that we introduced, is an iterative algorithm that automatically discovers the symmetries. And so it initializes each equivalence mapping to the identity. And then for each iteration to convergence, it's going to train a new set of optimal zero-shot coordination policies, given some set of, given the current set of equivalence mappings, and then extract symmetries from optimal policies. So let me say a little bit more about what that means. So intuition behind the discovery step in particular is, let's say you have some input goal G, and you have two optimal sender policies. So it is important that the policies are optimal. So pi1 sub I and pi1 sub j are both optimal sender policies learned, and they both take two different actions to communicate G. Then effectively what the algorithm can discover is that AI and AJ must be symmetric because two different optimal senders are using them to communicate the same goal. And so what we want to do is infer some mapping in order to transform one action to the other. And this is our equivalence mapping. And one of the nice things here is, we have quasi equivalence discovery. This quasi suggests that the equivalence mappings are learned from a learning perspective. And so it's based upon observations and actions of optimal agents. It doesn't have to adhere to the formal mathematical definition of symmetry. So even if the actions are approximately equivalent, then the agent can infer that they should be in the same equivalence class, that they're symmetric. And so more specifically, we infer these equivalence mappings. So let's say you have AI and AJ, which are encoded as one-hot vectors. And so what we want to do is learn some matrix phi ij that maps AI to, or maps AJ to AI. And it's a transformation matrix. So what we do is minimize the KL divergence between AI and some equivalence mapping over AJ. And phi ij is added to our set of equivalence mappings. So the implication here is that when we have some mapping, some equivalence mapping between two actions, that those actions are effectively belong to the same equivalence class. So the way this plays out in the referential game is, let's say I'm a sender agent who gets some goal G, and it takes an action AJ. So we have some equivalence mapping that will transform that to some action AI, and that's what the receiver sees. And then the receiver makes a prediction. So what this means is, if the receiver's prediction about G hat is correct, then the sender will learn that it can take action AJ in order to communicate goal G. And the receiver will learn that when it sees action AI, that means goal G. So now in a later iteration of this game, or in a later game rather, let's say now the sender takes AI. So before it took AJ, now it takes AI. We have a different equivalence mapping, which is JI, that maps this to AJ. So now both of the agents update their learning. The sender learns, not only can I take action AJ to communicate goal G, I can take action AI as well. So not only can I, signal my left hand, I can signal my right hand as well. And the receiver updates its learning to realize that when I see AJ, that also means the same goal. So you see how they kind of they end up being effectively equivalence classes. And so here is here's how QED performs on our discrete domain. So now what you see is each intent is mapped to an entire equivalence class. So like if you look at intent 1, on the left column, the sender policy, it's mapped to a uniform distribution over all of the actions in energy class. And then if you look at the receiver policy, what you see is that if it sees any of the actions 1 through 4, it knows that they all mean intent 1. And so there's only one unique way to map intents to equivalence classes over actions and be optimal. So the nice thing here is, if on the left side, you see 5 different sender receiver pairs that train through self-play. So again, their protocols are equivalent, but incompatible. And on the right side, you see 5 different sender receiver pairs that train through QED. And what happens is they effectively, if you look at what I have in the square, both sets of agents are able to do well with their training partner in self-play. But when we talk about zero-shot communication, so in cross-play, the degradation, there's a huge degradation in performance for agents trained through self-play, because again, their policies are equivalent but incompatible. Whereas when they train using QED, they're effectively all learning the same communication protocol. So even though I've never seen you before, we speak the same language, and I can talk to you zero-shot. There is some trade-off, however, because since QED basically learns probability mass over the entire action space, including the more costly actions, it ends up having a higher energy cost for the communication protocols than self-play does. But there's a huge performance, increase in performance in terms of communication. So then you may say, okay, we motivated this and we talked about two assumptions that get relaxed, one being the cheap talk and the other being discrete action. So what about the continuous channel setting? So this setting is more complex, and so we're still there's still much more progress to be made here. But the embodied referential game, now you have these articulated agents that generate entire motion trajectories, the sender agents, and the receiver agent is a discriminating network that is observing the trajectory. And so now the message is a motion trajectory, which has a high dimensional continuous state and action space. And the energy values are also continuous because we actually analytically compute some torque. So the energy values are also continuous. So this changes the complexity of the problem, and the message space becomes intractably large. So here we have not yet figured out how to infer or discover symmetries, but we train using self-play and third-party receiver training, which I'll quickly go over. And then the question in this evaluation is zero-shot communication possible in this continuous setting? So quickly, so you sample some goal from the set of goals using the prior. Pi 1 will get an observation and the goal and take an action and do this over t time steps, so generates an entire observation action sequence. The receiver agent Pi 2 will see the entire trajectory, and then the shared return still combines communication efficacy and then some kind of cost or effort penalty. But the penalty is now analytically computed. This is the torque, basically, of the motion trajectory. And so in order to train this, we still train using self-play, where sender-receiver pairs are just talking to one another. But we also have this additional third-party receiver training where we freeze all of the sender agents and we separate into a training set and a test set. And then we initialize a new receiver agent, and the receiver agent will train. So basically it learns this distillation policy from all the training senders, and it tries to zero-shot infer communication from the test senders. So this is how we test zero-shot communication in this setting. And then, so here I'm just gonna analyze the simplest communication task we did, which is 2 communicative intents. So if you look at the top middle, communicative 1 occurs about 67% of the time, and communicative intent 2 occurs about 33% of the time, so 2/3, 1/3. The y-axis is actually the training iteration, so it's a little bit counterintuitive. So the beginning of training starts at the top to the end of training at the bottom. The x-axis is the energy cost. So what we want to see is that, or what we'd expect to see is that intent 1 should always be to the left of intent 2 because it should be exerting the least amount of cost. And this is what we're seeing. The right side is a Gaussian that shows the distribution of energy costs at the very end of training, so at 10,000 at the bottom. And what you see here that's really important is that the Gaussian for intent 1 and the Gaussian for intent 2, their energy distributions don't overlap at all. So effectively what that means is very, very low joint entropy or very, very high mutual information, which is what the objective function is trying to optimize for. So this is great news. So so even if you don't see the motion trajectory at all, if I tell you which communicative goal I'm talking about, 1 or 2, you should be able to predict with high confidence where in the energy space that distribution, the action should lie or the trajectory should lie. So about how much energy the trajectory should exert. And if I tell you the amount of energy that's been exerted from the motion trajectory, which is the communicative gesture, if you will, then you should be able to, with high confidence, predict exactly which communicative intent was being conveyed without ever seeing the motion trajectory itself. The other thing here is that the Gaussians are pushed as far to the left as they can be, which suggests it's minimizing the energy exertion or the cost. So if they were moved further to the right, you'd still have high mutual information because they're not overlapping, but they would also be exerting high cost. But because they're pushed to the left, they're also trying to minimize cost. So this is a nice visualization to say that zero-shot communication is possible in principle, even with these continuous action protocols, at least for this simple task. Here's a visualization of 2 different communicative intents by 2 different sender agents. The same sender agent, but the 2 different communicative intents. You see it's kind of arbitrary, the motion, but it is emergent. But some open challenge, we introduced QED as a method for learning or discovering the equivalence classes over actions. And actually, it's more general than just the referential game. It discovers equivalence classes of policies. And then we explore optimization of continuous action protocols and some of the challenges with that. So some open challenges here is, again, within the thread of inferring optimal zero-shot protocols. One of the things I didn't show is it's very sensitive to where you initialize the protocol or the sender and receiver policies, like in terms of the protocol that gets learned. So guiding the policy search to more robustly converge to a global optimum, independent of the kind of where the policies are initialized. Also discovering, again, the symmetries in the continuous setting and trying to automatically discover this energy-based latent structure, because the entire zero-shot, the ability to talk to strangers is contingent upon understanding that the communicative intents are mapped to energy. And if the agents are not able to infer this energy latent variable, then they can't solve the zero-shot communication problem currently. And then learning human compatible protocols, of course, is an interesting question, because as you saw, the trajectories are quite arbitrary, but it's motivated by the idea of like gestures, for example. So if you wanted to communicate with humans zero-shot, then you'd need to think about something like including like a supervisory signal or like other realistic priors or inductive biases in order to aid with that. So, okay, I think that's it.
Thank you, Kalisha. Very cool
Thanks.
talk.
Thanks a lot.
I think we have some time for questions, and there's already some questions in the chat. So let's.
There's also, I think, a kind of still a clarifying question Wojciech typed here at the last moment.
Yeah, but I think Kalisha just said the same thing out loud at the same time I mentioned it, so never mind.
All right.
So then I guess you can feel free to upvote. There's no downvoting. Just upvote your ones you like the best. And then we can start at the top maybe. So Max, do you want to ask your question?
Yeah, sure. Thank you for the talk, Kalisha. So my question is about the problem framing. The question is simply, doesn't the implementation of a bias to encourage equilibrium selection effectively make the problem not really zero-shot because they had this coordinating signal to begin with?
So that's a good question. So zero-shot in the sense that the agents have never, so zero-shot with respect to the agent. So the agents have never encountered one another at training time, and they've never had the opportunity to indirectly, it's not like I talked to agent B and then you talk to agent B, so there's some kind of indirect contact. But so zero-shot with respect to the agent dimension, but with respect to the task itself, you do have to have some kind of common ground in order to expect to be able to reasonably generalize, in terms of the task. So kind of like, we may not have ever met, but there's some, conventions that exist within this culture, within this country, et cetera, that we can exploit in order to be able to talk to each other to more effectively and more efficiently.
So I think that really relates quite closely what I formulated later. I know it makes sense to try and directly tag on to this.
Sure,
so
go for it.
Essentially, if I understood correctly, the results that you are showing is that you now show that, okay, if you have two agents, even though they didn't train with each other, but they were both trained with QAD, then they will be able to indeed coordinate with another, communicate in this case.
Yes.
But now if you train one agent with QAD and another agent was trained somehow in self-play, you would still have the same problem, right? So it seems indeed that somehow you have resolved the issue at the individual level, but you will be remaining with somehow this issue at the algorithm selection level, if you will.
Right. Yeah. So it is true that there's an assumption here that it's basically like a meta equilibrium where you're assuming that the agents are using the same learning rule, and so and once they learn some communication protocol, then they don't have the incentive to diverge from the learning rule itself, which is this QED learning rule. But it is the case that if you started agents off, like if agents were training with, one was training with self-play or some other learning algorithm and another training with QED, then it would, you would not see this. So it is an underlying assumption that agents are using the same algorithm. And actually it could be one interesting open question, which is how do you now go to the more general case of like ad hoc teamwork or something like this, where you don't necessarily assume that agents are using the same learning algorithm.
Precisely. So indeed, I guess the logical follow-up question here is, so what does this lifting of the coordination problem to say the algorithm selection level, what does it really afford us now? Because if you're going to be encountering a random agent and you might not know how it's trained, then it doesn't directly help, but perhaps there are some other benefits about this.
I think oftentimes when I think it's still using, the other play objective is effectively adapting a self-play objective. And oftentimes when you look at work that's using self-play, it assumes that different agents are training using self-play. I don't think it's unreasonable to assume that agents can use the same learning algorithm. I do think, but to your point, I do think that it is the case that it may not be that every agent uses that. And I think that's where something like some kind of few shot adaptation, for example, could be quite useful. So it could be the case that I encounter another agent that did use the same learning rule as me at training time, and then zero shot, I'm able to communicate with that agent. But there might be other agents in the population that I'll encounter. Let's say I'm a car and I encounter some other car that didn't use that same learning rule. Then I think some algorithms for being able to try to quickly adapt to those agents would be helpful. And in particular, the main thing that it's doing here is learning some distribution over protocols. So given that we use the same learning rule and we have the same physical grounding of our environment, then we should learn the same distribution of communication protocols. So if you use self-play, then effectively you have a different distribution of protocols, that maybe you only have all your probability mass over one protocol. And so maybe part of what I'm trying to do when I try to adapt few shot is try to figure out how to adapt my probability distribution such that only one or only some small subset of the communication protocol should really have most of the probability mass.
Yeah, okay, thanks.
You're welcome.
Maybe then we'll switch to you, Ty, rather than having Franz ask two questions in a row.
Yeah, sorry. It's an interesting talk, but yeah.
Means he's really interested in it, right?
Yeah, that is. Sounds good.
Yutai, do you want to try and ask yours out loud, or do you want us to read it for you?
Yeah, you guys hear me now?
No, it's still pretty quiet. So either you need to yell into your mic, or we can try and read it, maybe. All right. So yeah, we'll read it. So it says. So QED is effectively a supervised learning approach to discovering symmetries. How do you ensure good coverage of the mapping then? Some kind of diversity bias, any examples of degenerate interesting solutions that can emerge?
Yeah, so that's a good question. So yes, so we do have an entropy, like a auxiliary loss, in order to in order to induce more diversity, because this is, and I mean, this is something that I ran into, thinking about also like the sample complexity, which is something that I'm still kind of working through, like, what from a theoretically analytical perspective, what can we expect with respect to this? Yeah, so it's a lot of it is basically hyperparameter tuning right now, in terms of just trying to figure out how much, because the entropy loss was used for exploration. So basically how much, so basically depending a lot on exploration in order to get agents to, different sender agents to converge on different, or to have different policies, that we can use in order to infer what the symmetries are. But I think that there are two thoughts that have come to my mind in terms of how to do this a bit more rigorously. One has to do with a more intelligent exploration policy, as opposed to just kind of using entropy and in order to try to maximize coverage in some reasonable region or something like this. And another actually has to do with the initialization of the policies. So because the policies are being initialized randomly, but it's not clear that would do, it's not entirely clear how that compares to like having like some kind of entropic bias, for example, to make sure that, yeah. So to the question, I think it's a very good question, but this is something that's still, I think, still trying to figure out largely.
Does that answer your question, Yutai?
Yeah. Says thank you. So hopefully.
Okay. So then we can go to Franz with his question then.
Yeah. All right. I'll go for it. Why not? That. Yeah. So I was thinking perhaps also I guess in terms of further scalability, like so high level. What I got here is that. Okay, there might be many symmetries. Somehow you bias the optimization in such a way that you're now making one a possible coordination protocol essentially globally optimal and therefore strictly preferred. But in general, this now still, I guess, is a type of DEC-POM-DP. And you know, solving these is provably NX complete. It might be that we're in a special case. Of course, you never know. So it might be that this is somehow an easier case. But yeah, it's not completely clear to me how we can essentially rely now on the agents actually always finding that same global optimum.
Yeah, I mean, so you're speaking about like from the optimization perspective as it's actually navigating the optimization landscape and actually converging on it. Yeah, no, you're right. I mean, that's actually the first thing I put as an open challenge because it's not that. I mean, that's a very big challenge. I mean, so actually 1 out of 10 times, for example. So when I was running it both in the discrete case and the continuous case, I think in the continuous case, but certainly in the discrete case, maybe 1 out of 10 times. From just random initializations, the agents converged on the globally optimal protocol. So it's a very big, I mean, it's a very big challenge in terms of how do you get the agents to reliably, robustly actually find that global optimum. And it's one that I think is really quite interesting, but it's not, it's still an open question.
Because if we reflect on the objective that you're optimizing, it seems likely that evolution would also put pressure on the same type of objectives, right? Maximizing mutual information, minimizing energy cost, somehow looking at the likelihood of goals. So to some extent, you would perhaps expect humans to somehow act as QED learners, right. But still somehow, so perhaps we are QED learners, but we converge to different local optima.
Right. I mean, yeah, and there are a lot of local optima, and yeah. So no, I mean, yeah, I think you're making a very good point. I mean, one thing that we did explore was trying to use some kind of curriculum, to try to like guide the learning. And that didn't completely find success with that. It's still not entirely clear what is the best curriculum to even use and how to, kind of instantiate it in such a way where it more robustly converges on kind of the globally optimal protocol. So yeah, no, I think you're very right. And I think and a challenge is that there are, I mean, I showed this picture where the optima are like exactly equivalent, for pedagogical purposes, but the reality of it is there might be one that's like here and then several that are like right here, and it's very easy to actually converge on a locally optimal protocol. And even when you look at examples of them, I actually do have a slide with some examples of suboptimal protocols, and they sometimes they can look very close to kind of what you might expect for the globally optimal one. So no, I think you raised a very good point, but it's not a question that we figured out the answer to as of yet.
No worries. We have some time left. Thanks.
You're welcome.
Yeah, interesting questions and lots of cool open problems to work on, but we should probably end it there.
Yeah.
So thanks again, Kalisha, for coming and giving a talk. Very cool stuff.
Thank you.
And
thank you all for having me and inviting me. I enjoyed it. And thanks for the great questions.
Of course, and everybody that is still listening on the recording or here, keep an eye out for future postings about the plan for the spring version of the seminar series.
Great. Thank you. This was awesome, Kalisha. Thanks everyone for joining.
Thank you.